Today we're going to continue to work on finding out whether infinite series converge or not. So we have two new tests, the ratio test and the nth root test. This one is going to be a really important one. This one isn't going to be used too often, but it works really well on special cases. So we're going to concentrate on the ratio test. So it says, let this infinite series have all positive terms, and let rho, and just concentrate on the black right now, let rho equal the limit as n approaches infinity of a sub n plus 1 over a sub n. So the n plus first term of the series divided by the nth term. Then, if rho turns out to be less than 1, the series converges. If rho turns out to be greater than 1, it diverges. Unfortunately, if rho equals 1, the test is inconclusive. Basically, the test fails. You'd have to look for something else. Now, the nth root test is the exact same thing, except instead of taking the ratio of the n plus first term to the nth term, you take the nth root of the nth term. So let's right now just concentrate on the ratio test. And I'm going to do a proof because this one is not so intuitive that that would be true. I'll just do the ratio test proof. And it's going to be kind of a hard one, so really try to concentrate and understand what's happening. We have to do it in three cases. One, if rho is less than 1. Well, if rho is less than 1, think about the number line. There's always a number in between two real numbers. So I know if rho is less than 1, if you look down the number line, here's rho and here's 1, there's going to be an r, a number r somewhere in between there. So this is on a number line. I could have a less than and a less than here. Now we have to go to this limit. We know if this rho equals this limit, then for every epsilon greater than 0, no matter how small, there exists a value n such that the difference between a sub n plus 1 over a sub n and rho is less than epsilon whenever n is greater than n. So this is where you really have to concentrate, because what this is really telling you is no matter how small you want to get, you can get this ratio right here, you can get it as close to rho as you want. So there's some difference between rho and r. R minus rho is the distance between there. So that means I can get a sub n plus 1 over a sub n. I can get that ratio somewhere in between here. Because whatever that distance is, I can always get the distance between here and here to be less than that. That's what this is saying. So the conclusion is, if we just look at this, that a sub n plus 1 over a sub n is going to be less than r for all values of n greater than n. Or if I just multiply, I can say a sub n plus 1 is less than r times a sub n for n greater than n. So we're going to start, actually all of these should have been greater than or equal to n. So we'll start right at big N. And we're going going to put big N in here. And what do we get? We get A sub n plus 1 is less than R times A sub big N. And now I'm going to do it. A sub n plus 2 is less than R A sub n plus 1. But since A sub n plus 1 is less than this, I can say which is less than R times this, or R squared A sub n. And then I can do it again. A sub n plus 3 is less than R A sub n plus 2. And if I look what A sub n plus 2 is, it's less than this. So R times that is going to be less than R cubed A sub n. And then I can just keep doing this all the way through. And what I form is a series. If I add up this plus this plus this, what series do I get? The series is A sub n times R plus R squared plus R cubed plus dot, dot, dot. And since R is less than 1, and it's a number, this is a geometric series. And we know, since R is less than 1, that it converges. A sub n is just a number, so it's not going to affect the convergence. And look at this other series formed by these terms. That's the series A sub k from k equals n plus 1 to infinity. That's the series we're trying to find out whether it converges or not. We're starting at a different point, but that doesn't really affect the convergence. So what do we see? We've got a series here that term for term is less than this series, which converges. So by the comparison test, we can say that ours converges. So we've proven the first part, if rho is less than 1. That's the hardest one. Now, what if rho is greater than 1? So what if I can put rho right here on the number line and rho is greater than 1? Well, again, since we can pick A sub n plus 1 over A sub n as close to rho as I want to get, I know that I can fit it somewhere in between here. Which means that for all that, and this is only for n greater than n. If you get far enough out in the series, I know that this is going to be true. So I'm just going to concentrate on this and say, and multiply by A sub n, and I get A sub n is less than A sub n plus 1 for all values of n greater than big N. And what is that kind of telling you? In this series, the terms keep getting bigger and bigger. Well, if the terms keep getting bigger and bigger, could the limit as n approach infinity of A sub n equal 0? There's no way. If the terms keep getting bigger and they're positive, they can never go to 0. Therefore, by the very first test we learned, the nth term test, we know that the terms have to go to 0. So I can say the series A sub n diverges. And now we've passed that one, or we've proven it. Now, for the third one, when rho equals 1, what I'm going to do on that one is I'm going to take two different series. I'm going to take the series 1 over n, and I'm going to take the series 1 over n squared, and I'm going to do the ratio test on both of them. So what does the ratio test say? Take the limit as n approaches infinity of the n plus first term, 1 over n plus 1, divided by the nth term. Well, with a little bit of division there, we get n over n plus 1, and we get 1. So now try this one. We do the same thing and we say rho equals the limit as n approaches infinity of 1 over n plus 1 squared. The n plus first term divided by the nth term. And then I get the limit as n approaches infinity of n squared over, if I square that out, I get n squared plus 2n plus 1. Well, I only have to look at the highest power of n. I can ignore this, and I get 1. So what did I find? That I got rho equals 1 for this series, which converges, and I got rho equals 1 for this series, which diverges. So obviously, having rho equals 1 is inconclusive. Sometimes we could get something that converges and sometimes diverges. So that's that. Now, one thing I hope you can see that is so nice about both of these tests is they don't make you go to another series. We don't need another series to compare it with. That was one of the hardest things to do. These are just looking at the series that we're interested in. Now, I'm not going to do the proof for this one. I think you probably have seen enough proof because it's a fairly similar type of proof. Okay, so let's look at a few examples and then we'll be done with this test. So what you're going to find is this test is really nice for factorials. It's really nice for n to some power. And it's really nice for some number to the nth power. Things that we don't have good comparisons to do. So if I look at this one, I see a lot of good things that are pointing me towards the ratio test. So I say rho equals the limit as n approaches infinity, and I take the n plus first term, which just means plugging n plus 1 in wherever you see n. This is going to be n plus 1 plus 1, so it's going to be n plus 2 factorial. And then you divide it by the nth term. Well, when you divide it by the nth term, it's like multiplying by the reciprocal. So we might as well do that right away. So the reciprocal, and you're first looking and saying, no way am I ever going to be able to do that limit. It looks too complicated. But nice things happen. N plus 1 factorial over n plus 2 factorial. N plus 2 factorial is really just n plus 2 times n plus 1 factorial. It's n plus 2 times n plus 1 times n. So what happens is this cancels with this, and you just get an n plus 2. In the numerator, we have n squared plus 2n plus 1. In the denominator, we have n squared times n plus 2, or n cubed plus 2n squared. So what we see, oh, I forgot to take the limit. The limit as n approaches infinity, since this power, n squared, the largest power in the numerator, is larger than this, we know we have 0. And since 0 is certainly less than 1, the ratio test says that does converge. We didn't have to look at another series to compare to it, which I think you're probably happy, because that would be hard to find something that compares. Okay, let's try another one. This time I use k instead of n. It still should work just fine. So we say rho equals the limit as k approaches infinity. And now we just take the k plus first term, so putting k plus 1 in for k, and divide it by this kth term, which again is going to be multiplying by the reciprocal. So rho equals the limit as k approaches infinity. Let's see what happens. 2 to the k over 2 to the k plus 1 is really just 1/2. And that 1/2 I could bring right out front, and what's left? K squared plus lower powers. I don't even have to multiply it out. They're lower powers of k over k squared. So all of this is just going to be 1. So rho is equal to 1/2, which is less than 1. So I can say that this series converges. Again, what you're kind of seeing in this one, factorials are really powerful. That tends to make these ratios small, these things you're adding up, especially as n gets really large. And the same thing here. If you have a number to the kth power, that's stronger than taking a number and squaring it. Even if that number gets really big, 2 to the 1,000th power is going to be bigger by quite a bit than 1,000 squared. But now, in number 3, we're getting into a battle between having factorials over 1,000 to the nth power. So we've got a tougher battle here. Let's see what we can do. We can say rho is the limit as n approaches infinity. Now we have to make this n plus 1 factorial over 1,000 to the n plus 1. And I have to divide by this or multiply by its reciprocal, which is 100 to the n over n factorial. Well, cancellation works really nice. N plus 1 factorial over n factorial, knowing that this is n plus 1 times n factorial, I just am left with n plus 1. And 1,000 to the nth over 1,000 to the n plus 1 is 1,000. Well, as n approaches infinity, this is going to go to infinity, which is certainly greater than 1. Therefore, this series diverges by the ratio test. So it seems that factorials are more powerful than taking to the nth power. Because I think you could see, even if this number was 1 trillion instead of 1,000, the only difference is this would be 1 trillion. It would still go to infinity, and it still would diverge. So now we're going to come to the ultimate battle, the battle between n factorial and n to the n. Not like 1 trillion to the n, but n itself is also going towards infinity. So let's see what happens. Let rho equals the limit as n approaches infinity. And we get n plus 1 to the n plus 1 over n plus 1 factorial. And then I have to divide it by this or multiply by the reciprocal. Well, what cancels? N factorial over n plus 1 factorial would just leave n plus 1 in the denominator. So what we have is rho equals the limit as n approaches infinity. Now, n plus 1 to the n plus 1 over n plus 1 is just n plus 1 to the n. And then you're over n to the n. So altogether, you get the limit as n approaches infinity. Since they're both to the n plus 1 power, or both to the nth power, you can go n plus 1 over n to the n. So this is going to be getting really close to 1, and this is going to be really getting close to infinity. So we have like an indeterminate form. But this is something that we did a while ago. If I write this as 1 plus 1 over n to the n, that's that famous limit that we found converged to e. And since e is greater than 1, we can say that this diverges. So I think what we found is that n to the nth power is even stronger than n factorial as far as how big those numbers are getting. Okay, so this one, where you have your a sub n is something to the nth power. This is the one case where that nth root test is really going to work nicely. And it's about the only case that it really works nicely. So what we're going to do is say rho equals the limit as n approaches infinity of the nth root of this to the nth power. Well, that's just going to wipe out the powers, and you're just going to get 3n plus 7 over 4n minus 2. And if we just look at the highest powers of n, we see that this is equal to 3/4. And 3/4 is less than 1, therefore this series converges by the nth root test. And I think, without actually doing another problem, you could see if I had had a 5 here instead of a 3, this would have turned out to be 5/4, and then this series would have ended up diverging. Okay, well this one doesn't look too bad. Let's try it. Let's try the ratio test. The limit as n approaches infinity of n plus 1 over n plus 1 squared plus 1 divided by this or multiplied by the reciprocal. And so what do you get? You get n plus 1 times n squared plus 1, which is n cubed plus lower powers of n. I'm just going to say lower powers of n because I think they're going to end up not affecting our answer. And what are you going to get here if you multiply n times this? You're going to get n cubed plus some lower powers of n. When you take this limit, you're going to ignore all these lower powers of n, and you get 1. So what happens? The ratio test failed. So usually, when people learn the ratio test, they kind of like it and say, I'm going to use it on all my series. But they don't always work. And almost always, they're not going to work on one that you should have done a comparison test. This one you should have looked at right away and said, that looks a lot like 1 over n, because you have n over n squared. And you would have done this with the comparison test or the limit comparison test. In this case, since these terms are smaller than something that diverges, we'd have to use the limit comparison test. So this is a quick review from yesterday. The limit comparison test would take this and divide it by this. So you get n squared over n squared plus 1. And you get a limit, you get rho to be 1. In this case, that's a number, not 0 or infinity, so they compare favorably, so you would say this diverges. So don't count on the ratio test always working. So we have all these different tests. That's the end of the test for series that have all positive terms in them. So we're going to go on to series that have some negative terms in tomorrow.